In the present video, I will discuss regarding mapping functions. So we have to copy some set of blocks from the cache into the main memory. So this particular function is called as mapping function. When a memory word that is not present in the cache but which is requested by the host or the processor, the block containing the required information has to be brought into the cache from the main memory. If the cache is full, so then the cache control hardware must decide which respective block need to be removed to create the space for the new block. So this decision on many factors and the set of rules governing this respective operation is called as replacement algorithm. So the mapping function will decide which respective blocks from the cache will be mapped into the main memory. So in the mapping function, we are having the cache size need to be considered while mapping the blocks from the cache into the main memory. So we can consider one perspective as cache utilization level. So with respect to whether the cache utilization level is in the medium mode or low, or if it is 100% reached. So if it is cache is 100% filled, or else the cache is reached to high watermark level, or else the cache is reached to low watermark level, or else the cache utilization level is between low as well as high watermark level. So since the main memory is large compared to the cache, so we have to careful while mapping the blocks from the main memory into the cache. So we can make use of three different techniques. So we can assume that the consecutive address refer to the consecutive words in the memory. So in order to consider these mapping functions or different mapping functions, so we can assume a cache having 128 blocks. We can assume the cache with 128 blocks, and these 128 blocks can be mapped into the main memory. So the main memory size it consisting of around 4095 blocks, 0 to 4095 blocks. That means, so it consisting of around 4096 blocks. So main memory has 64K word, and which is organized as 4K blocks of 16 words each. So now we'll consider different mapping functions as the first one is direct mapping, the second method is associate mapping, and the third method is set associate mapping. So these mapping functions will decide which respective blocks of the cache can be mapped into the main memory. So how we can map out from the main memory which respective block can be copied into the cache. And we know that the cache size is around 128 blocks. The cache consisting of around 128 blocks, and the main memory which is consisting of around 4096 blocks, that is 4096 blocks. So we know that all the blocks from the main memory cannot be mapped into the cache, because the size of the cache is comparatively less because within the cache it consisting of around 128 blocks, but in the case of main memory it consisting of 4096 blocks. So all the blocks from the main memory cannot be mapped into the cache. So that means the respective blocks, only few respective blocks can be mapped into the cache. So next we'll take one by one different mapping functions like direct mapping, associate mapping, and set associate mapping. So first we'll take direct mapping. So in the case of direct mapping, the block J of the main memory maps onto block J modulo 128. So we can consider while mapping, we can consider modulo function or modulus function, and I can say that block J of the main memory, can be mapped into block J modulo 128 of the cache. When the memory blocks 0, 128, 256 are loaded into the cache, the block is stored in the cache block 0. So that means 0 modulo 128 is 0, 128 modulo 128 is 0, 256 modulo 120 is also 0. So I can say that 0, 128, 256 etc. are those blocks from the main memory can be mapped into the cache. So the block is stored in cache block 0. So these blocks of informations from the main memory can be mapped into the cache, that is block 0 of the cache. Similarly, memory block 1, 129, 257 are stored in cache block 1. So that means 1 modulo 128, that is 1. 129 modulo 128, that is 1. Remainder is 1. 257 modulo 128. So again remainder is 1. So main memory blocks 1, 129, 257 are mapped into cache block 1. So here what is a major drawback is it's a contention problem or overhead problem may arise when the cache is full. So whenever the cache is full, but I need to map the other some set of blocks from the main memory into the cache. So at that instant, contention or overloading may arise with respect to the cache. When more than one memory block is mapped onto a given cache block position. So we know that we are mapping more than one block from the main memory into the cache. We are mapping more than one block, like 0 is the block 0 of main memory is mapped into block 0 of cache. 128, that 128th block from the main memory is also mapped into block 0 of cache. 256 is also mapped into block 0. Similarly, block 1 is also mapped into block 1 of the cache. 129 is also mapped into block 1 of the cache. 256 is also mapped into block 1 of the cache. So that means more than one memory block is mapped into the same block of the cache. So the contention is resolved by allowing the new block to override the currently resident block. So how I can overcome from contention problem? So we can override the information. So memory address determines placement of blocks in the cache. So we are having the memory address information which will specify the respective block location within the cache. In the case of direct mapping, we know that block 0, block 128, block 256, so on, can be mapped into block 0 of the main memory. Block 0 of the main memory. So we have to consider block J. I have to consider block J modulo 128. So first I'll take, so this is nothing but blocks of the main memory. So now I'll take block 0 modulo 128. So that means 0. Similarly, remainder is 0. 128 modulo 128. Remainder is 0. So similarly, 256 modulo 128. Remainder is 0. So I can say that from the main memory, from the main memory, block 0 is mapped into block 0 of the cache. Block 128 of the main memory is mapped into block 0 of the cache, and 256, that is the 256th block from the main memory, is mapped into block 0 of the cache. So here we can clearly observe that more than one block is mapped into the same block within the cache. So therefore there will be a chance of contention. There will be a chances of contention, or problem of contention may arise with respect to the direct mapping. So in the case of direct mapping, we know the equation as J modulo 128. So now I'll consider block 1, block 129, block 129 and block 257. So these are the blocks of main memory. So now we can use the equation J modulo 128, that is J is nothing but 1 modulo 128. So reminder, I'll get it as 1. So 129 modulo 128. So that is 1. So 257 modulo 128. So again 1. So I can say that block 1 of the main memory is mapped into block 1 of the cache. Block 129 of the main memory is mapped into block 1 of the cache. So 256 block is mapped into block 1 of the cache. So the diagram shows how the main memory blocks are mapped into the cache using direct map function or direct mapping function. So here we know that in the cache we are having blocks from 0 to 127, so total 128 blocks. So with respect to the main memory, we are having the total number of blocks as 0 to 4095. So total we are having 4096 blocks. So we know that we cannot map all the blocks, that is 4096 into cache, because within the cache we are having only 128 blocks, but with respect to the main memory we are having 4096 blocks. So as per the direct direct mapping function, so we know that block 0 is mapped into block 0 of the cache. Block 128 is mapped into block 0 of the cache. So similarly, block 256 is also mapped into block 0 of the cache. The next one is 3968. So that respective block is also mapped into block 0 of the cache. So that is block 0 is mapped into block 0. Block 128 of the main memory is mapped into block 0 of the cache, and block 256 is mapped into block 0 of the cache. Similarly, 3968 block 3968 block is also mapped into block 0 of the cache. Similarly, we are having the next set of blocks as block 1 is mapped into block 1 of the cache. So next is block 129 is mapped into block 1 of the cache, and block 257 is also mapped into block 1 of the cache. So this is how we can map some respective blocks from the main memory into the cache, so that the processor can directly access the informations from the cache rather than from the main memory. So here we are having the tag bits, that means around 5-bit tag bits, around 5-bit tag bits. We are having 5-bit tag bits, 7 bits block address and 4-bit word informations. So we know that in the main memory address main memory address, which consisting of or which will reserve around 5 bits to specify the tags, and which will reserve around 7 bits to specify the block address, as well as 4 bits to specify the world of informations. So the main memory address is divided into 3 fields. So as I mentioned before, it consisting of lower order 4 bits, so which is used in order to select one of 16 words in the blocks. So this lower order informations or 4-bit information is used in order to select any one of the words, but what is the size of that word? That is 16-bit. So similarly, it consisting of 7-bit cache block field. So this 7-bit cache block field determines the cache position in which the new block must be stored. So the 7-bit block field or cache block field specifies the cache position in which the new block can be stored. The last memory address information, that is around 5 bits tag field. So this 5-bit tag field specifies the memory address of block is stored in 5-bit tag field associated with the cache location. So it specifies 5 bits memory address of the block is stored in 5 tag bits associated with the cache location. The major drawback of direct mapping is contention problem. So we have to overcome from this contention problem. That means many number of blocks are trying to map to the single block within the cache. So to make the mapping function more flexible, so we can adopt one more method or strategy called as associate mapping. So in the case of associate mapping, a main memory block can be placed into any cache block. So the main memory block can be placed into any cache block position. So the mapping function with respect to associate mapping, there is no need to justify a specific empty block in the cache when a new block arises. So it is not mandatory that we have to specify any empty blocks or free blocks within the cache whenever we are mapping any block from the main memory. So it can be placed in any free cache block. So we are not reserving any free space while mapping the blocks from the main memory into the cache because the blocks from the main memory can be placed in any free blocks within the cache. So we are having around 16-bit address informations. 12 tag bits are required to identify a memory block when it is resident within the cache. The tag bits of an address received from the processor are compared with the tag bits of each block of the cache to check which particular tag bits are mapped or matched. So if it is matched, the respective block of the main memory can be mapped into the respective block of the cache. So we are using 12 tag bits. So we are using around 12 tag bits which identify a memory block when it is resolved in the cache. So tag bits of an address received from the processor are compared to the tag bits of each block of the cache. So how to compare? So initially for respective blocks we are assigning the tag bits. Respective blocks we are assigning the tag bits. So these tag bits of an address received from the processor are compared to the tag bits of each blocks of the cache. So when comparison is done, that means when the comparison is matched, so at that instant the respective block can be mapped into the respective block of the cache. So in the case of associate mapping, so we have to compare the tag bits. So we have to compare the tag bits. So these tag bits are assigned by the processor. The tag bits of an address received from the processor are compared with the tag bits of each block of the cache. So to check whether the tag bits are mapped or not. So here each memory block is associated with any free cache block within the cache. So therefore the space in the cache is used more efficiently. So we can use the space within the cache. We can use the space within the cache which can be used more efficiently. I can say that the space is used more efficiently in the case of associate mapping. A new block brought into the cache has to replace the existing cache block only if the cache is full. So if suppose cache is 100% full, or cache utilization level reaches to its 100% value, so that instant then only we can overwrite the informations. We can overwrite the informations. That means, so if the cache is full, if it is 100% full and we have to copy a new block into the cache, so that instant we have to replace the existing cache block. So we have to replace the existing cache block. Since we do not attach a specific cache block to any main memory block, we need an algorithm to replace an existing cache block. So these replacement algorithm may be either, so we may need to use replacement algorithm, so that may be either LRU or MRU. So whenever the cache reaches to its 100%, so that instant some respective pages or blocks need to be copied from the cache into the main memory. So for that we have to use one algorithm which is called as replacement algorithm. So that replacement algorithm is either LRU, that is least recently used algorithm, which works with the principle of first in first out. So which works with the principle of first in first out. So, and one more algorithm is most recently used algorithm, which decides, that means in the case of replacement algorithm, so it decides some respective blocks or pages are most recently used by the processor, and such respective pages will not be accessed in future. So, and those set of blocks or pages can be deleted from the cache, or it can be moved from the cache into the main memory. So that is nothing but MRU, or most recently used algorithm. So we are having, with respect to the associate mapping, we are having around 12 tag bits, 12 bits to specify the tag value, and 4 bits is used in order to specify the word. The cost of an associative cache is higher than the direct mapping, because we need to search all the 128 tag patterns to determine whether a given memory block exists in the cache or not. So this kind of search is called as associative search. So we have to search all 128 tags of the cache blocks in order to identify, or in order to check to which particular blocks of the main memory can be mapped into the which particular block of the cache. And this search is called as associative search. That search is called as associative search. Associative search. To obtain better performance, search should be done parallelly. Fully associative method gives the best performance, however, is complex to implement. Each tag line requires circuitry to compare the desired address with the tag field. So here now we'll consider the diagram for associative mapping. In order to achieve more flexibility compared with direct mapping method, we can adopt one more mapping technique called as associative mapping. So in the case of associative mapping, which adopts a different strategy in which a main memory block can be placed into any cache block position. So the mapping is shown in the diagram. Here, so we need to identify the tag bits. So initially the tag bits will be assigned by the processor to individual blocks of the main memory. So each and every the tag bits need to be compared with the tag bits of the cache. So suppose I can give the tag bit value as the block 0, I will assign it as some tag bit value, some tag bit value. So block 1 is some tag bit value. Similarly, block 27 is some tag bit value. So whenever there is a mapping need to be considered from the main memory, or the block of data need to be copied from the main memory into the cache. So that instant the processor will issue the tag bits to the blocks of informations within the main memory. Suppose the block 0 need to be mapped into the cache. So I'll take one condition here. The block 0 need to be mapped into the cache. And at that instant the tag bit will be assigned. Suppose I will take it as the tag bit as 1, 2, 3. And the processor will issue the tag bit value as 1, 2, 3 to block 0. And suppose here I am having one more block, that is block 2, so which consisting of tag bit as 1, 2, 3. So now we have to go for associative searching with respect to the tag bits. Initially this 1, 2, 3 is compared with block 0. If it is not matching, it will compare with the next block. If it is not matching, it will go to the next one. So now here the tag bits are mapped. So now I can say that the block 0 of the main memory can be mapped into block 2 of the cache. So each and every time we have to check the respective tag bits which was assigned by the processor with the tag bits which is already assigned with respect to the cache. So now I'll take one more condition. Suppose I need to map block 1. So it consisting of the tag bit as x, y, z, and I'll assume this tag bit of 127 as x, y, z. Some value I'll take randomly. I'll consider it as x, y, z. So now I need to map block 1 information of the main memory into the cache. So first I'll compare this block 1 tag bit xyz with block 0. It is not matching. Block 1 I'll compare. Second comparison, it is not matching. Block 2 is also not matching. 3 is not matching. So on, and I'll come to 127th. At that time it's matching. So we considered around 128 searches. So total we matched around 128 tag bits. Out of 128, 127th till 127th it was not successful. So the last one, 128th, the tag bits are mapped or matched. So that instant I can say that block 1 can be mapped into block 127 of the cache. So now the major drawback of associative mapping is associative search. So associative search. The major associative search. The major drawback in the case of associative mapping is associative search. That is, the time taken in order to search the tag bits or in order to compare the tag bits is large or more, I can say. So that is the major drawback of associative mapping. If the respective tag bits is available in the last block, so have to check all the previous blocks tag bits or have to compare all the previous block tag bits with respect to the cache. So this is a major drawback of associative mapping. The drawback of direct mapping is contention problem. The drawback of associative mapping is associative search, or it takes longer time in order to search the tag bits. So in order to overcome from these two drawbacks, so we can adopt one more mapping function, so which is called as set associative mapping. So in order to overcome from contention problem as well as in order to overcome from the associative search problem, so we can adopt one more technique or advanced technique called as set associative mapping. So I can say that in the case of set associative mapping, it's a combination of direct and associative mapping. The block of the cache are grouped into sets. So we can combine or we can combine blocks of informations into a single set. The mapping allows a block of the main memory to reside in any block of the specified set. So for I'll combine 2 or 3 blocks together and I'll assign I'll group it as one set. So within the set, the mapping function allows a block of the main memory to map into any block of the specified set. The cache has 2 blocks per set. So memory block 0, 64, 128, 4032 maps into cache set 0. The cache can occupy either of the 2 block position within the set. So in the case of set associative mapping, we can use 6 bits to specify the set field, which determines which set of the cache contains the desired block, followed by 6-bit tag field. The tag field of the address is compared to the tag fields of 2 different blocks in the set. The comparison is done to check if the desired block is present or not. So we can combine the advantages of direct mapping as well as the flexibilities of associative mapping, and we can construct a new mapping technique called as set associative mapping. So in the case of set associative mapping, the blocks of the cache are grouped into sets. So we know that in the case of set associative mapping, the blocks of the cache. So set 0 consisting of block 0 as well as block 1. Block 0 as well as block 1. And the mapping function allows a block of main memory to reside in any one of the block within the specified set. So while mapping either the respective block, if I need to map within set 0, suppose I need to map to set 0, the mapping function allows, or set associative mapping function allows, to map the block of informations from the main memory either into block 0 or else block 1. So we are having the choice that either the block can be mapped into block 0 or else block 1. So that is, the block of main memory are associated with sets of the cache. So therefore to some extent contention problem is resolved now. So the contention, we can overcome from the contention problem. That means the blocks, suppose if I need to map one respective block to set 0, I am having the option that we can either map to block 0 or block 1. So an example of this technique for considering two blocks per set is two blocks per set. Here the memory block 0, 64, 128, 4032 are mapped into cache set 0. So we can assume some set of blocks like block 0, 64, 128, 4032 are mapped into set 0. Similarly, block 1, 65, 129, 4033 are mapped into set 1 and so on. Any memory block can occupy either of the two cache blocks position within the set. So totally we are having around 64 sets. So we know that we are having within each set it consisting of two blocks and total we are having within the cache we are having 128 blocks. So therefore 128 by 2 is equal to 64 sets. So that is set 0 to set 63. So total 64 sets. So totally there are 64 sets and 6-bit set field of the address which determines which set of the cache might contain the desired block. So we need to check or we need to consider the 6 bits set field. So this set value is nothing but which is around 6 bits to determine which set of the cache might contain the desired block. The tag field of the address is then compared to the tag field of the two blocks. So first initially the set field is compared, after that the tag fields will be compared. So in order to decide to which particular block can be mapped into the which particular block of the cache. So compared with the associative mapping, so in the case of associative mapping we have to consider around 120 maximum 128 searches, but in the case of set associative mapping, so we need to consider only 64 searches. So therefore the search time is reduced, so thus reducing the design cost. So the number of blocks per set can be selected in the entire structure in order to identify the actual requirement of the system. So we can either select 4 blocks per set and if you are using 4 blocks per set, we need to use 5-bit set field or 8 blocks per set. So it can be implemented using 4-bit set field and so on. But as the blocks per set are increased, the tag fields, so number of tags required within the each set is also increases, which increases the size of associative search. The extreme case of 128 blocks per set. So the extreme case means I can consider around 128 blocks per set corresponds to fully associative technique. No need of set field here because all the entire 128 blocks are combined within a single set, where as one block per set is a direct map method. A cache that has k blocks per set is referred as k-way set associative cache. Suppose the cache consisting of k blocks per set. Cache consisting of cache blocks per set, which is called as k-way set associative mapping. So in the case of associative mapping, we can overcome from the contention problem which was arised with respect to direct mapping function, and we can also overcome from the associative search. That means associative search is reduced now. So in the case of associative mapping, there were around 128 associative searches, but in the case of set associative mapping, so there are around only 64 associative searches can be considered. So in the case of set associative mapping is an alternate as well as better solution to the other two methods. The bigger the set is, the better the performance, but complex as well as expensive one. So after mapping technique, so we have to control the informations. So for that we are using one valid bit. We are using one valid bit which is used in order to provide, which is used within each block to indicate whether the block contains valid data or not. So within each block it consisting of a valid bit which specifies whether the block contains valid data or not. The valid bits are set to 0 when power is initially applied or when main memory is loaded with new programs and data from the disk. So transfers between the main memory and the disk are carried out by the DMA mechanism. So the data can be exchanged between the main memory as well as the disk can be done by considering blocks of informations can be exchanged. So in terms of blocks of data, so that is we can make use of DMA concept. So direct memory access. Can consider the mechanism called as DMA or direct memory access. So the valid bit of a particular cache block is set to 1 the first time this block is loaded from the main memory. So initially the valid bit is set to 0 when the power is initially applied, or else whenever the information is loaded with the new programs, and this valid bit information is set to 1 the first time this block is loaded from the main memory. Whenever a main memory block is updated by the source that bypasses the cache, a check is made to determine whether the block being loaded is currently in the cache or not. So after mapping from the main memory into the block or a cache block I can say, so we have to check whether the entire informations are correctly mapped into the cache or not. If it exists, its valid bit is clear to ensure that there is no data loss appeared with respect to the cache even if the block is mapped from the main memory. So next we'll take advantages of set associative mapping. The first advantage is contention problem of direct mapping is solved by having few choices for block placement. So because we are having two options to while mapping the main memory blocks into the cache. So suppose if you are having or if you are considering two blocks within each set. So we are having two options within which the blocks of informations can be mapped from the main memory into the cache. So that we can avoid contention problem. We can avoid the contention problem which was occurred with respect to direct mapping. So the hardware cost is decreased by reducing the size of the associative search. So we can reduce associative search. In the case of set associative search, there will be around 64 searches, but in the case of set associative search, there will be around 64 searches maximum number, and but in the case of associative mapping, so there will be around 128 searches. So therefore, the hardware cost with respect to set associative mapping is decreased by reducing the size of associative search.